Hey everybody, so this is just a follow-up video on two different videos that I made deriving Newton's second law. I had some questions about it, some really good questions, talking about issues between this statement, this is the equation that I derived in the two videos, and its correspondence with classical mechanics. Now classically, we've got these two different equations. The first one is just the definition of momentum. It says, look, there's this thing called position. We can talk about the position of a particle. We take its time derivative. We get the momentum. We multiply that by mass. That's just the definition of momentum. And then over here, this is what they call Newton's second law. The time derivative of the momentum is the negative. Sorry, my negative got a little squished in there. Gradient, or here I'm doing partial derivatives because I'm working in one dimension, of your potential energy function, which is a function of the position of your particle. I suppose possibly over time. I'm not going to deal with that here. But notice that this is a closed system. We've got two variables, x and p, and we've got two differential equations to solve them. The position is just some function of time, and the momentum is just some function of time. So we can solve this and figure out what our particles are doing for all time classically. Now what's interesting is that we get analogies to this in quantum mechanics. It's meaningless to talk about the position of a particle quantum mechanically, but we do often talk about the expectation value, or the expected value of the position. And lo and behold, we have that the time derivative of the expected value of the position is equal to the expected value of the momentum over m. This statement's kind of rigged. I'm not going to talk about that here, but this is an interesting derivation. We find that the time derivative of the expected value of the momentum is negative. The expected value, okay cool, we're working with quantum mechanics, of the partial with respect to x of the potential energy, which is a function of position. Look at this, that's exactly what we have here, except with expectation values, which is what we want. That makes it quantum mechanical, right? There is an issue though. When we look at things classically, we're solving for x and p. There's no other variables showing up in our differential equations, right? The potential energy is a function of position. There's just going to be a bunch of x variables somewhere in here, no matter how complicated the function becomes. It's still a closed system, but here, we would want to be solving for the expected value of position and the expected value of the momentum, but our potential energy function is a function of the position of the particle, which is a problem. What we want would be this, right? This is what we want. The only difference is that the potential energy would be a function of the expected value of position. Then we'd have a closed system of differential equations. Two differential equations, two unknowns. Now, we're not screwed. There is something we can do to make that expected value of position show up. But some interesting things happen along the way, and that is what I want to talk about today in this video. Okay, so the way that we're going to get around this is to look at the Taylor expansion of the potential energy function around the point A equals the expectation value of position. Maybe I'll just put a little line over here. So if we write this out, we have the sum from n equals 0 to infinity of the nth derivative evaluated at the expected value of position divided by n factorial times x minus the expected value. And that's just an expansion. That's just first year calculus. Instead of our function f, we have our potential energy, function of position, and we want to expand around the point the expected value of the position. Now immediately you should see the derivative showing up. That's good. We want some derivative somewhere. Awesome. And notice that these derivatives are going to be derivatives with respect to x, right? We're taking the derivatives here with respect to the variable that we started with. So if we write out a couple terms, what we're going to find is the 0th derivative evaluated at the expected value. 0 factorial is just 1. Anything to the power of 0 is just 1. So that's our first term. Okay, awesome. Plus, we have the first derivative with respect to x. And this is evaluate. I'm going to write it. I'll write it out like this for this line. Evaluated at the expectation value, right? So it's a partial with respect to x, but then we evaluate it, and then we get x minus the expected value just to the power of 1, okay? Then our second term is going to be the second partial derivative, and now I'm just going to write the expected value in here, right? But we know we take the derivatives first, then evaluate it at the expected value for the position. So now we have squared, and we're going to have other terms. These are the ones of interest to us. So we don't have the potential energy showing up in our equation. We have the partial derivative of the potential energy with respect to x. So we might as well go ahead and take our partial derivative term by term here and see what we're going to get. Well, this is a constant, right? We've evaluated it at the expectation value of x. All of our pure x's that would have been in our equation here have turned into expectation value. So let me give you an example. We're working with a spring, let's just say. Right, so our potential energy, let's just say, is proportional to x squared. Right, so if we evaluate it at the expected value, we now have a statement that is proportional to the expected value of position squared. And so if we take the partial derivative of this now, after we've evaluated, it's going to go to 0, right? Be proportional to 0, because the partial derivative, we could write it in here, sends this guy to 0. Okay, that's what I mean. So this thing is just going to be 0. Awesome. Here, again, we've taken our derivatives. It's different in the Taylor expansion, because the Taylor expansion says take the derivatives then evaluate it at the point. But now we've already done that evaluation, so that gets pulled out of our derivative. So we're left with the partial of x, the partial of the potential with respect to x. This term, if we take the derivative of it, is simply 1. Okay, so that's looking promising. If only all of this would go to 0. Sorry, excuse my typos. If only this would all go to 0, then we'd be golden. Skipping to the punchline, but the punchline is it doesn't go to 0, and that's where quantum mechanics steps in. This guy, if we pull out our term involving the potential, because again, it doesn't see this partial derivative, we just have that the second derivative is like this. This term, I'm really sorry, this needed to be divided by 2. From our Taylor expansion, I forgot about the 2 factorial, which is simply 2. So what happens here is this 2 comes down, and we simply have the first power that we did. It's the chain rule, right? Derivative of the outside, 2 times the inside, then times the derivative of the inside is just 1. Okay, so these guys cancel, and then we have plus our other terms, and we know how to take our derivatives. So they didn't go away, but what happens when we take the expectation value? Because furthermore, not only do we not just have the potential energy function, we have the partial derivative of the potential energy function, but beyond that, we also have this expected value. So if we go ahead and look at that, what we're going to find, partial of the potential energy with respect to x is equal to, our 0 we don't care about. This is our expected value evaluated at the expected value of position. Perfect. This is what we wanted. So this term is the interesting one. So what happens here, this is a constant, so we can rewrite this. The guy we wanted, actually, you know what? I'm going to focus on this on another sheet of paper. Okay, so here's where we left off. This is just a constant, right? So we can, if we have a constant times a function and we want to find the expected value, you can still say that that is the expected value of your constant times the expected value of your function. We don't even need to write the expected value. It's a little bit redundant, but we want that to show up in our final solution. So, actually, you know what? It doesn't even matter because of what's about to happen. But the point is, this is a constant. We can pull it out from the expected value of this function. This term is the one that I really care about because I have a function minus a constant, I can write that as the expected value of this function minus this constant, right? The expected value of an expected value is just the expected value. So this whole thing is 0. And if you don't trust me, if you're a little bit suspicious, that's good. But remember the definition of the expected value. So if we go back to our definition of the expected value, I mean, we can think of this as an operator, right? The position variable and the position operator are the same thing. So from our definition, this is just the integral over all of space of our wave function. I've written better size in my day. Times x minus our constant, because a constant operator is just the constant itself. It's the same thing, sure, okay. Times our wave function again over all space. But we can split this integral up into two parts. We have our integral over all space of our wave function times x dx minus, this is just a constant, we can pull it out of the next integral, the integral over all space of our wave function conjugated times our wave function. But by normalization, this is just 1. And by definition, this is the expected value of x. So again, we find the expected value minus the expected value, which is equal to 0. So either way, this whole term is going to go to 0 in our previous equation. So this whole term goes to 0. Unfortunately, it's not so simple for the other terms. Let me go back and write out a couple other terms. I should have just written out this term in the first place, but here we are. So here is what we have after we take our partial derivative, right? We have this term here. And then we know when we take the expected value of this, it's going to look like this. The term we wanted, wonderful. This term goes to 0, but this term and all of the higher order terms survive. So this is what we're going to have, coming back to our original proof, or our original paper at the very least. We're going to have this term involving the third derivative. So this is what we're going to be finally left with, plus fourth derivative, fifth derivative, da 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 da. And you can split these up however you want. You know, again, this is a constant as far as the expected value is concerned. We can pull it out of there and sure, write it however you want to write it. But the bottom line is, and this is important, is if you have a potential energy function that is quadratic, and only quadratic, right? Linear is a special case of quadratic, okay. When you take your third derivative, this whole thing is going to vanish. And all you're going to be left with is this term right here. Coming back to our original equation. Why don't I write that out again, one more time. Okay, so I've written out our equation again. If we could have stopped here, everything is golden. But we end up having these other terms. I didn't have the minus sign here because I just simply hadn't written it yet. But if we look at our original equation here, right, there's a minus sign. So all I did was put that minus sign in here. That's all that's going on. Now this is a minus sign minus all these other terms involving the fourth derivative, fifth derivative, sixth derivative. But again, if you have a potential energy function that is purely quadratic, these other terms go away. And all that we're left with is an exact analogy for Newton's second law derived solely from quantum mechanics, right? We talk about the expected value of momentum and the expected value of position, but that's all that we ever talk about in quantum mechanics. And things behave exactly as we would expect with our classical intuition. However, if you have a potential energy function that is anything, a polynomial of a higher order than 2, if you have some sort of sinusoidal potential energy function, or, you know, even worse, those all can be written as polynomials if you want to think of it that way, but they're all infinite order polynomials, right? So they are still higher order polynomials than 2. And they are going to pick up these other terms, these other quantum forces, they're sometimes called, right? Because the potential energy tells us about our forces. And there will be corrections to Newton's second law. So that wraps up this discussion on corrections to Newton's second law. As far as quantum mechanics is concerned at a non-relativistic level, which was what we would want for classical. Classical mechanics is non-relativistic. You can find an exact analogy to classical mechanics as long as your potential energy function is quadratic. Please let me know if you have any more questions. The whole reason I made this video is because of a fantastic question from a subscriber, and I'd be happy to make more videos answering some of your questions. I try and keep the mathematics to something that a second-year university student would understand, but I'm happy to talk about some more advanced topics as well. Thank you very much for watching. I really hope you enjoyed it, and I'll talk to you guys again soon.